In this video we study a powerful primitive in distributed computing, the so-called shared coin. We show how to use a cryptographic tool, namely threshold cryptography, to implement a shared coin. If you don't know what these terms mean, don't worry. We will explain them first. Let's start with the definition of a shared coin. Nodes in distributed systems often need to make random decisions. Each node can generate randomness independently, but how can the nodes make the same random decision? What we would like to have is the following. All nodes that make up the distributed system together run a distributed protocol to make a random decision, and the outcome of the random decision is 0 or 1, both with constant probability. In this case, we say that the protocol is a shared coin protocol. Note that the two probabilities do not necessarily need to sum up to 1, which means that the shared coin protocol may fail. However, it can only fail with constant probability, so regardless of the probabilities, it only takes a constant number of trials until all nodes together create a random coin toss successfully. Now we understand what a shared coin is. Let's now take a look at the other term that we mentioned in the beginning, threshold cryptography, or more specifically, threshold secret sharing. For integer parameters t and n, where t is at most n, a secret is protected using a threshold secret sharing scheme if any t keys of n are sufficient to reveal the secret, but using fewer than t keys reveals nothing about the secret. In the example here, there are n equals 3 parties and t equals 2, so any two of the 3 parties can together reveal the secret. We also introduce the notion of a signature here. Alice, the lady at the top, can use her private key to add a digital signature to the message so that the receiving party can verify that the message was signed by Alice exactly in the form that the message was received, that is, it is not possible that some party manipulated the message. We will now briefly explain how threshold secret sharing can be implemented. Let's say Alice has a secret S that is a real number. Alice then picks t-1 random real numbers and creates a polynomial of degree t-1, with the chosen random numbers as the coefficients and the term independent of x being the secret S. That is, the secret is revealed when evaluating the polynomial at x equals 0. Alice then chooses n distinct non-zero numbers and then pairs up each of these numbers with the value of the polynomial at these numbers. Given these pairs, how can the secret be reconstructed? If you wish to think about this now, please pause the video. We will continue here shortly. Did you figure it out? Since it is a polynomial of degree t-1, t points on the polynomial are sufficient to reconstruct the polynomial. Rather than calculating all terms, Lagrange's interpolation formula can be used to derive the value at x equals 0, that is, the secret itself. That's a simple mechanism to build a threshold secret sharing scheme. However, there is one thing we need to fix. We said that the secret and all parameters are real numbers, which are not really suitable for computers with bounded memory. In practice, numbers from a Galois field would be used instead. Now that we understand the basics of threshold secret sharing, let's see how we can use it. Given a distributed system, we want to give all nodes access to a random bit. Let's keep it simple and say that Alice acts as the dealer, that is, Alice generates the secret bit, creates the random polynomial, and calculates n points on the polynomial. She then sends 1 point on the polynomial to each node. How can the nodes use this threshold shared secret? Let's say the nodes run some distributed algorithm and now they need a shared coin. The algorithm works as long as fewer than half of all nodes may be faulty. We assume the worst case here and let 2 out of 5 nodes crash right now. In this case, it should be possible for the remaining nodes to obtain the secret bit. To this end, the nodes simply broadcast their points on the polynomial. Once they have collected 3 points, they can use Lagrange's interpolation formula to determine the secret shared coin bit. What if the faulty nodes do not just crash? What if they are malicious and try to prevent the other nodes from obtaining a shared coin? Alice can protect the integrity of the points on the polynomial by appending a signature to each of them. Malicious nodes can then only decide to withhold them but not manipulate them. It is further important that Alice can share the points in such a way that no malicious nodes can learn about the points before they are being used, for example, by encrypting them with the node's public keys before sending them to the nodes. A bigger challenge is to implement the same mechanism without a centralized dealer, which must be trusted here and is a single point of failure. This is out of scope for this video. We just note that there are cryptographic tools that make this possible. Let's summarize what we've learned. We defined the notion of a shared coin. We then introduced the concept of threshold secret sharing, and then we showed how threshold secret sharing can be used to implement a shared coin, making it possible for nodes in a distributed system to jointly make random decisions. Thanks for watching.